we're going to go into two main talks now, consensus hierarchies and mergeable consensus. There was a third one on braid, but we're going to run out of time, so we'll do it in the future. And yeah, we have the room. We want to get out of here around 5, so should have plenty of time for that. Yeah, and so the last part is talking about composition. And so there's, in particular, 2 things that we want to talk about in terms of composition. One is hierarchy, and the other is mergeable consensus. And so we'll start with talking about hierarchies and ways in which different kind of constructions of different kinds of hierarchies of protocols are used today, and some potential different ways of building new ones. And we'll also talk about a set of interesting problems around mergeable consensus, where we think about how consensus networks can split and subdivide and then can merge back together, or potentially even start on their own and merge together. Great. So let's start with hierarchy. Hierarchy is a very common thing in distributed systems and computing. It's used all over the place to be able to scale systems. And blockchains are no different. So to actually reach the level of performance guarantees that we want out of blockchains, we will achieve that through certain kinds of hierarchies. And first of all, let's motivate the problem, right? So we're certainly interested in things going faster, so we want to increase the transaction throughput. We want to deal with the communication complexity by assigning the communication complexity to different subsets. We also want to potentially deal with partition tolerance. So today, a lot of consensus protocols, especially blockchains, cease to function when they go into some partition state. So if there's a large network with a lot of parties and so on, and they're operating across the internet, and there's some network partition, then they would get isolated and wouldn't be able to talk to each other. And so in those moments today, most blockchains will continue operating as if nothing had happened, and maybe mining would get more difficult and so on, but it would still effectively go on. And you might have to go back and revert a whole bunch of state once the partition heals. So it would be really great to have systems that can tolerate those kinds of long-running partitions, because they're a reality in our systems and networks. And most internet systems and most centralized architectures handle that just fine. So that's a high bar for where we want consensus protocols to scale to. Another thing we care about is risk isolation. So this is creating options to trade off security and performance. So there are all kinds of security properties that tax the performance of a system, whether it's by introducing additional rounds, or slowing things down, or introducing a lot of overhead in terms of the proofs involved and so on. So we would like to have a system that can give participants options between the security level they want and the performance guarantees that they want in terms of when the transaction is clear. Not all transactions are made equal, effectively. Some transactions are moving and dealing with vastly larger quantities of value. And then, another pretty important part here is governance. So a lot of systems have different governance systems and would like to dealing with large global internet-wide things, all sorts of choices and decisions will emerge. And for the most part, we've seen these governance decisions and dissent turn into whole network forks, where then it becomes a bit difficult to deal with state. And so far, in terms of assets, that's been fine. We've seen the forks of Ethereum and Bitcoin, the assets sort of get duplicated. It's kind of like a crazy event. And in some cases, we have even seen some of those networks eventually be shut down. But it gets drastically harder to think about governance and forks when you're dealing with state that is not just counts of an asset. When you're dealing with state that is state in an application. If you were going through the Ethereum to Ethereum Classic fork or the Bitcoin to Bitcoin Cash fork, and you had a smart contract that had state dealing with some application, think of like a chat system. Suddenly you would have to reason about your chat system being on one network or another. And like suddenly you wouldn't be able to interact with some set of people unless you switched which chain you're on. And that's the sort of thing that should never happen to application developers. You shouldn't have to reason about that level of breakages, and you should be able to have some way of handling those governance issues transparently for software developers. We talked about consensus bottleneck, and this is big motivation in terms of scalability, and in terms of the internet, partitions do happen. There was a case where I think South Africa was isolated from the rest of the internet for quite a while, and then all kinds of Bitcoin transactions happened, and they had to then later get overturned many hours after when they regained access to the network again. So network partitions are reality, and we want state and financial systems that can handle them gracefully. So now it becomes all these systems become a lot easier to think about if we consider consensus groups. Consider a network of consensus protocols, of related network consensus protocols, where they're effectively running some version of the same protocol, but maybe have different properties. So this might be the network diameter. It might be different. So for example, one protocol might be running inside of a single city, so it could go drastically faster than other protocols, right? The block time could be in the single milliseconds or tens of milliseconds, as opposed to a block time that has to go across the entire world. We're in that point where in the single seconds, those are kind of the limits. Then other properties that vary might be membership limits. So some parts of the network might be completely open membership, anybody can join. Some other parts of the network might not be so open. So some applications might choose to run in an environment where the consensus is protected by some sort of permissioning. And so this gives you a way to reason through how might you mix the benefits of open membership systems and chains with the security guarantees that come from some permissioning, security and performance guarantees that come from some kind of permissioning. Then you just have to reason about the state migrating into and out of that space. So there's a lot of these kinds of properties that we may want to vary across these systems. Probably the key thing to reason about is state. At the end of the day, you might have the same smart contract across all these different consensus protocols across the entire network, and you might have a different copy of the smart contract living in each one, and they would potentially have different versions of the state. And so at that point, that's something that can be handled directly in the contract or the application. You would have to reason through, the developer of that smart contract would have to reason through what does it mean to have a partition in the state. This is exactly what a lot of developers handle today in normal standard applications, so it's not something completely foreign. It's just something that is harder to do. Many applications don't care about this. Many applications can just spawn many copies of themselves, and it's fine, and you can merge them back together. But some applications do want to reason carefully about how the state gets partitioned. But in general, it just becomes pretty easy to think about these sort of consensus groups. Now, we talked about kind of the internet and partitioning in the internet and what happens when you lose connectivity. You can think of overlaying creating these consensus groups to match the topology of the internet. So you could imagine ISPs or the structure of connectivity in ISPs sort of implying the sets of consensus groups that you might want. So this could be one per continent. You could have these like large regions that are right underneath some sort of global consensus. Then you would have potentially a per country thing because there's all kinds of policies. So this relates back to the governance question. There might be a whole bunch of policies that indicate certain kinds of transactions or contracts can occur in one region but not another. And you could get down all the way to the two cities. So that's one example. But of course, there are other ways that you might want to shard it. By the way, I should flag that in this kind of network of consensus protocols, I do mean related consensus protocols. So you might have a broader meta network of different groups of consensus protocols that might still interact. So think of this as Ethereum and Bitcoin interacting or something like that. But that's a separate story. It's related, but I just want to treat that separately. In our case, we want to deal with a group of closely related protocols. This basically means it's probably running the exact same code, just with different parameters. So yeah, we talked about matching the network topology, and this is something that what this might look like. You might have certain groups that interact very closely together and might have pretty frequent transactions, and then you might have some larger groups that kind of form across those. So this mirrors what already happens today in the internet and in major systems and applications, which is the emergence of regions. So if you look at the architectures of groups like cloud systems like Amazon's or Google's, they already have a sophisticated set of, there's about 7 data centers in the world that each map to one of the main regions. Then there are these like other sub-regions that get broken down from that. There's and you can go all the way to points of presence in ISPs very close to users and so on. So you want we want to move our usage of state replication, consensus, and all this tech to be able to deal with the realities of the network underneath the hood. And Hierarchy is a very clean way to do that. It also helps us to think about matching the use cases. So for example, the performance and security guarantees of something like social media, where you might be recording an image and sending it to other parties, and the applications that want to facilitate that have to deal with maybe getting consensus over the fact that this happened, on what the bits are, and so on, but then could maybe store all of the actual information, all of the bits of the image or the movie separately, not necessarily in consensus. It's one way of operating, and it has certain kinds of security guarantees where the level is not as high as, say, for example, a high-frequency trading market. So imagine a single data center where there's a lot of different parties that want to trade things in the order of milliseconds. That's going on today, and it happens. And these systems have drastically higher security requirements, and certainly couldn't deal with a block time that was seconds slow. That's just absolutely infeasible. So these are two pretty different use cases, both in the speed of the consensus in terms of social media should operate across the planet, and this high-frequency trading stuff should be able to operate in milliseconds, not have to wait seconds for confirmations. Now, of course, you might say, hey, you could do all of this off-chain and so on and create extremely complicated constructions. But at some point, it becomes just drastically easier to model the entire system as just saying, hey, what if we had a local consensus that could go drastically faster? And of course, if we go the other direction and we start thinking about things like interplanetary communications, certainly we don't want an 8-minute block time for something like, for most applications. But certain kinds of movements of state might require that, or we might be fine with. It's kind of funny that the Bitcoin block time is 10 minutes. But so of course, this is not new. We see a lot of this already in the world. It just is within the cloud. So you can think of how the Borg system maintains state. And of course, this is not Byzantine, but there's already consensus operating across managing and distributing huge workloads. And so that's, Borg was the system at Google that did this, which eventually turned into Kubernetes. And so you can think of that already being an example of how you would use some kind of consensus to manage a distributed set of pool of workers to do operations, but also log and have some notion of the transactions on that system, meaning when some worker node comes online, goes offline, migrating work, or restarting work, and all that kind of stuff. Again, not new. Things like two-phase commit, things like, I think the current buzzword is multi-data center data consistency or something like that, which really just means two-phase commit across the data center. It's the same kind of story. Hierarchy applies. And the blockchain systems are already starting to do this. So we've heard about Plasma. We've heard about the ETH 2.0 set of chains and sharding. So this is a structure where they have a main chain at the top that does staking, a beacon chain that handles all the randomness, then I think on the order of hundreds of shards that are going to be separating the state, and then the smart contracts would be living within one of those shards and operating there. Now, I think in this case, all of these shards are global, so they would be probably running at the same speed. And this is just done to be able to parallelize the state of Ethereum. So this means drastically increase the throughput, by order of the shard number, and so you could horizontally scale Ethereum this way once the sharding is in place. But you could easily see how this could move to what we were talking about before, which is then starting to have shards that have all these other different kind of properties, having faster block times, having different kind of security guarantees, and so on. And it turns out that even older than that, the sidechains idea is a version of the same thing. You can think of that whole effort, not clear how successful it was, but that whole effort was a way of reasoning about hierarchy and moving of state across these different chains that were along Bitcoin. I want to talk about hierarchy of security levels for a moment. And let's consider two protocols. A fast protocol that finalizes in a few seconds. So you can think of current blockchains. By most system standards, that's really slow. But hey, let's call that fast. And a slow protocol that finalizes in a day or longer. So imagine if we took the head of a chain and just printed it on a newspaper every day. And if we print the head of a chain on a newspaper, that creates something that is quite hard to change. If you had millions of copies of newspapers, say the New York Times printed the head of Ethereum daily, you would now have an extremely difficult to change log. Because not only would you have to compromise the entire Ethereum network and try to convince all of these nodes to pretend the other chain didn't exist, but now you would have to go and find all the copies of the New York Times that have been printed and destroy them or hide them in some way. So you could imagine building some federated thing around all the newspapers in the world coming together to create one of the most immutable things to ever have existed, which is just printing the heads of some chain across the planet. And you could come up with some federated protocol by which disagreements between these newspapers are discovered, and you could probably resolve that in some way. But I use it as a toy example to show, hey, you could have a relatively fast protocol that finalizes quickly, but which if dealing with proof of stake might have certain concerns around long-range attacks, where hey, there's all these potential problems that might emerge when miners can go back and fork the chain and reorg to years ago. All those problems would completely go away if you had a way of checkpointing into this slower consensus protocol. So by tiering the security, you can afford to go much faster and sacrifice a little bit of the long range, or not sacrifice, but you don't have to solve those problems at every layer. Now you can even think of a drastically slower protocol that finalizes yearly, where we take the state and then we etch it into diamonds or DNA or something, and we embed it into the world in some way that becomes extremely difficult to overturn, and we now have something that's truly immutable, right? So when people tell me that the Bitcoin blockchain is immutable, it's like, well, it's all bits in a hard drive anyway. If we EMP the surface of the planet, that's going to be kind of gone. But if we put it into diamonds or stone or whatever, and we throw it into the ocean, then that's really hard to change. Might be hard to read, so the read time hard to verify if you don't have the entire chain. Certainly with DNA, you could actually dump the entire chain into that. There's amazing performance in terms of compressing information into DNA. And on the other side of the spectrum, we could go very fast. We could have consensus protocols that finalize in a few milliseconds. In that, again, that's in intra-data center usually. But there are a lot of cases, especially in markets. And so we think about it in terms of storage markets. If you had an extremely fast system that is trading storage or trading options on storage or things like that, and you have all these contracts dealing with storage as a commodity, and they want to be able to deal with it very quickly, then you start needing something that is both secure, but it also can go extremely quickly. And hey, it turns out blockchains already do a kind of checkpointing. We just don't like to talk about it, or at least people in the proof of work maximalist community don't like acknowledging that blockchain checkpointing is going on. So I call this entire kind of structure, it's this progressive immutability that you get out of consensus. and that if we built protocols this way, and maybe you don't need all these layers, but that allows you to change the requirements for your protocols. You don't have to solve all the problems at every layer. So let's talk about Bitcoin for a moment. I claim that it really is a combination of two protocols. Protocol number one is a proof of work Nakamoto consensus, and protocol number two is a Twitter Byzantine agreement, where you have to deal with people noticing things missing in the chain, and then people getting mad and yelling at each other. And then if a reorg is needed, then miners call each other, and they agree, and they reorg the chain. And this has happened multiple times. This is not so rare that it's just considered. We know of this happening.
Out-of-band communication.
Exactly. So you can think of, there's been a case where there was, I think, an accidental software update that forked Bitcoin, where a whole bunch of nodes went into one fork and a bunch of nodes went into another. That was in, I think, 2013. We've also had these isolated subnets that I mentioned. South Africa Bitcoin nodes were just sailing on by as if nothing had happened. It just got really hard to mine for a while. But other than that, sure, yeah, that transaction clears. Double spend, I've never heard of it. And then we also have these currency hard forks where, in Bitcoin we don't have to deal with sharding application state in the same way that Ethereum does. But certainly more and more sophisticated applications will have to deal with this. And so we should get ahead of this problem. It turns out that the Zcash community considered putting in an automatic checkpointing system into the, oh, sorry, I forgot to mention, Bitcoin does do checkpointing, and they did it in the code base. There are these hard-coded checkpoints for the blockchain right in the code that kept being added. But I think somebody pointed out that that's not believing in just proof of work as the sole arbiter of what's the holy consensus, but that is a product of this Twitter Byzantine agreement kind of construction, or maybe GitHub Byzantine agreement. And then I think a lot of developers just stopped recording checkpoints out of that. And so it was an explicit statement saying, if tomorrow another chain appeared that went back years, we would take it, which for a moment might seem like a statement, pro proof of work and so on, but it's actually dooming Bitcoin. Because if that happened, all of the asset holders who have been using the economy of Bitcoin would then just say, great, we will fork this network, and we'll call it Bitcoin Classic or something, and we'll continue as if nothing had happened, because most asset holders that use Bitcoin for something real want an economy, not a proof of work chain. So I think this is just this denial that's going on around what's really going on, which is this two-tiered system of security, where one part of the security is given by this extremely difficult to revert proof of work, but which is not completely safe, and then a higher order human-level agreement, similar to the ISP stuff that we were discussing before on these tussles that happen. That's just natural, which is a fine protocol. It works. We've seen it work. And that's on the order of hours or days, which is reasonable. Now that we acknowledge that this is going on, we might want to think of other layers going in between. Maybe we want some in-between checkpointing system that automatically gathers the checkpoints. So instead of dealing with developers putting checkpoints into the code, we could have it automatically happen in software. Some blockchains have been doing this, so Zcash considered it. I believe they ended up not doing it. Maybe they did, I don't recall. But there is a whole thread where they discuss how this would work, how many block height, what the block height would be at which they would start this automatic checkpointing, and how to deal with a moment where you notice that there's actually a different chain that has completely forked. Do you halt? Do you throw it back to the user, and so on? At the end of the day, these systems are live, and these errors do happen, and so they should be handled in software at some point. And the higher level protocol should acknowledge that this kind of problem can occur. There's another work which I think is Tortoise and the Hare, I think, which is a two-protocol that deals with this very explicitly and says there's a slow, more secure consensus, and there's a fast, optimistic consensus that kind of races ahead. and this just formalizes that notion. But I believe that doesn't deal with the larger scale network partitions that we would also want to deal with. So in Falcon, we think about this a lot because we would like to be able to have, this is not for first versions, but kind of more longer term. We would like to be able to deal with that scale of partition. We would want to be able to have all your data stored in Falcon available to you, whether or not your country happens to be connected to another country that hour, right? And so we think about how can we reasonably do these partitions of state, and how can we model that so that subsets of the network can remain operational and can mutate state safely through that partition. And even right now, Falcon is sort of a combination of four. We might describe it as four meta protocols. One protocol that we heard about today is expected consensus. This is the leader election and proof of stake inspired protocol. We saw the demo of the chain happening. The other protocol is we call it storage power consensus, which is we use these proofs of useful work to generate a power table, and from that power table, we then feed that information into expected consensus. But that power table and that actual useful work is a slower, harder level of security that's committing the head of the chain to the actual storage that people are providing. So that means in order to overturn that consensus, parties would have to amass huge amounts of storage and kind of gain power through the system. Not necessarily to overturn, but to double spend through that consensus. And so you get this automatic checkpointing that happens with the useful work through this part of the protocol. And hey, maybe we want just automatic checkpointing in software just directly as a failsafe. We don't have that yet, but this is something that we are considering. And at the end of the day, we acknowledge that the Falcon improvement proposal process is a form of consensus. This is a human-level consensus that where all groups come together and discuss potentials for improvement and so on. This is the same as Ethereum. Ethereum has that level of consensus as well. So now, I want to talk a little bit about splitting and merging state, because it turns out that this is a very easy problem if you sort of step back. I think all of these solutions that we mentioned already do it. And so at first, thinking about these different consensus groups seems complicated, but the problem ends up being quite simple. We can think of each consensus group as having a tag, a unique tag. So and you might observe that diagram happens to have 2 2s. I didn't make it. But pretend that all of those tags are unique. Then you just bin the network state into the corresponding groups where they belong. So if this is a mapping onto the internet topology, then the state would go into the right part of the tree where it belongs. And if that's overcrowded, then maybe you split off and automatically start generating subtrees. Then you can reason about how transactions move state from one group to another. So if you want to go from group I to group J, then you have to think of how a transaction would clear through both. So from a child to a parent, that's easy. From across siblings, that would involve potentially clearing through the parent. There are some more optimized versions of this that people have been writing about them that get away without that. But this is very simple, straightforward, kind of straw man example of how to think about this. And then you would want to also move state across the tree. So you should be able to do even transactions that effectively do a two-phase commit across the parents. So if you want to move something from one side of the world, then you kind of go across. Now, of course, you can optimize this by saying, hey, you really only need to involve 6, 2, and 9. You don't have to involve 7 and 5. But it's just a way of thinking about it. And that's it. So this is so we talked about just how you might create a family of consensus protocols and reason about the state moving. And by the way, this is as in all things software, presenting this to the actual developers as a primitive can make this a really powerful tool for and make it actually useful, as opposed to pretending that this network would never split or anything like that, and then having to deal with terrible performance and guarantees. It's much better to build a model that actually lets the users select where they want to operate. Great, and then thank you. That's it. Questions? Any questions? Yeah, go ahead. So that would mean, suppose you have two contracts. So let's think about it with money. So you have money in, say, let's use this example. You have money in consensus group 5. So you have some consensus network, and you can think of it as a single shard or a single chain, and you have some money there, and you would want to move it from 5 to 11. And so maybe 5 is a really fast consensus inside of a data center, but the security level that you want is not, you don't want to hold all of your assets there because that data center could be compromised. So you want to move it to some much slower consensus or something. Maybe you want to move it to 2, like the top level thing. Then that would require a transaction that commits the movement of the state from 5 to 2. Now with money, it's easy to think about. You can just think of account balances. You kind of lock it in 1 first. You then propose it into 2, and then you commit it in both spots, and then you can reason about the state moving that way. But it gets a lot harder to think about for applications. So certain kinds of applications would have to reason about what does it mean to merge state this way. So if this was again a chat system of some sort, and these were potentially governing things like friend lists or something like that, then you have to reason about what does it mean to deal with local state merging that way. So this is where the CRDT's work comes in. So CRDTs is this entire field of how do you do eventually consistent or convergent data structures, and you build applications that just naturally work with that. Think of Google Docs, I guess, as a great example. Google Docs, you can have a document in one laptop and in another. You can type. It works. Your updates go from this computer to another, and they synchronize. Now, do that safely and with high security on assets that have a lot of value. You have to work a bit harder to make that work, but you could reasonably get to that point. And you could think of some of these groups as splitting, right? So you could imagine going into a plane and being able to continue transacting and using all your applications, and still then getting out of that plane and merging all the state back. Does that kind of clear up what the statement? Great.
So the geo-partitioning that you talked about,
Yep.
there's a single things, right? In normal large-scale distributed systems, or if you were sharding, you might shard geographically so that if there's a partition, I continue to have likelihood of availability, and if I'm traveling to the other side of the world, I might request it to migrate, so I would be, if there was a partition, I'd be able to work remotely. Are you looking at, or other systems looking at, taking advantage of that kind of thing to achieve, in the case of your country getting cut off from the internet, still being able to spend your wallet and not have it be double spent, because it's only allowed on this side of the partition, not the larger side on the other.
Yeah, and this, you don't want to deal with, you shouldn't think of this as kind of having different currencies necessarily, right? Like this isn't taking dollars and turning them into euros and then having to go back. Just think about dollars that are spendable in a certain region at a certain point in time, right? So say that you actually want all of the dollars to be kind of secured by the top level consensus where everything is going well, but then you move a fraction of that into wherever you are right now. So if you're in the US at the moment, or maybe it's dollars, and so that way you keep most of the dollars in the US because that's where it comes from, that's where the issuer is. But then if you go and travel to Europe, then you can you can do this automatically. You can pre-commit, you can pre-move some subset of the dollars into that region so that you can use it. And this happens. I mean, you've probably been and what happens right now is that credit card companies basically take the risk, right? Like they have these pre-authorization lists where they give you a credit card and you know what that credit card, what bank it's related to. And so in a moment where somebody swipes a credit card in an operation, if they can't, for whatever reason, reach the the issuer on the other side of the world, like they can still clear that locally, and it'll get settled later. So that's kind of what this means. So you would see state moving automatically following users traveling. So for that, money is one case. Another case might be data. So I don't know if you've noticed this, but depending on the region in which your Google Docs server is, you can either get really fast or really slow operations. So if most of your group is in like the US and you go to another country, then just Google Docs gets slower, like noticeably slower. And this is just a straightforward thing that they could fix on their end. But that part of what's going on is they're doing like kind of commits all the way to the US. And this could be adjusted by just migrating some subset of that to allow some local committing in the data center that's closer to you without having to commit all the way. And I'm sure they do this for a lot of their systems. It's just maybe a couple like slip by and, oh yeah, when you type, it actually has to go a transatlantic communication before it's committed.
Isn't this what interchain projects are actually kind of doing in some sense? Because each blockchain project has their own consensus mechanism, and by having the Cosmos or Tortoise, isn't that?
Yeah. So I think, and this is sort of what, I think that's more like this, which is, it is similar and it is related, and what's sort of developing is an internet of blockchains where you think of the data in one chain and the data in another chain and transactions going on here and here, and then you find ways of mapping between the two, and then people say, hey, we're sick of doing n-squared things, let's build standards. Aren't standards nice? Isn't this like what we've been doing? And then that happens, and so that's occurring. But I think those don't go as far as allowing the kind of automatic contract migration that I'm talking about. Like you would want to be able to take a smart contract in one platform and then just be able to migrate it into another. So maybe with things like Substrate, you'll be able to do this. If that becomes the standard that a lot of people use, or Agoric, then people would be able to do this kind of migration across the chain seamlessly. Yeah. Yep.
So the other question I have is, given the Stellar presentation earlier, here in some sense you've got a graph, but they were sort of doing a general graph. Sorry, you have a tree. They were doing a general graph. Do you have an analogy or comparison?
Yeah. So actually, funny story. When I started thinking about hierarchy of consensus protocols, I was actually talking to David about Stellar, and he was like writing the Stellar paper at the time, and he like showed me this graph which had a graph, and I immediately understood it to be like a hierarchy of like countries, but he was talking about a different graph, and so yeah, it's similar. What I think kind of like a next step of that is thinking through how you could do that voting of the state in Stellar in this kind of way where you allow subset of the network to commit some subset of the state on their own before it gets externalized to the rest of the network, because they can. And I guess this already sort of happens automatically, right? With the quorum slices.
No, it doesn't. But I mean, you could imagine multiple instances of consensus. Like you have kind of side chains that are like subsets of the validators, and then you have a main net that's like all of them.
Yeah. So if each of these was a consensus, a Stellar instance, and then you would have had a way of moving the values in the state from one Stellar to another.
Yeah. So it becomes slow to move across the main net and operate locally once you preloaded one.
Yeah, exactly. And I think right now with most systems, you would end up running like two instances of the thing, or have a program that runs two versions of the protocol side by side, and then kind of reasons through it. I think what we'll move towards is systems that, a single instance of the thing is going to be able to understand which network they're in and how to reason about how to move the state. But it'll probably take a while till we get there.
I mean, not to harp on this, but I kind of feel like this is where like two-phase commit is like pretty useful. Like one of the underappreciated aspects of blockchain is that like you have this like super reliable like public thing where you can pre-sign things and have a timeout. So that could essentially be like a super reliable two-phase commit program. So it's the potential to basically commit transactions atomically across systems that have no other way of interoperating and don't know anything about each other.
Yeah, and I am thinking of two-phase commit as the thing that moves state from one shard to another. And I think sidechains did that.
It might not even be moving money across the blockchain. It could be like, booking space in a rail car from New York to Chicago and another rail car from like Chicago to LA. And like you don't want your goods to go only halfway, but these two rail companies have like completely different systems, right? And so the thing is like you're going to do this payment and buy these things, but you only want to buy both or neither.
Yeah.
And if the rail companies themselves have this extremely opaque pricing that's like similar to airlines where two people sitting next to each other pay like 10 times the difference in price.
Yeah.
And so what you just want is like some hook that allows you to say, great, I want to buy that and I want you to sign a pre-commit that's good for 10 minutes to like sell that to me, but I want you to bundle it with this other pre-commit that's like completely opaque to you, and just everybody agrees that if the transaction commits on the mainnet, that then these two other things happen.
Yep. Yeah, and so that would, and I think that's, I don't think that's even that far away. Like you could implement this pretty straightforward with most of these the chains that currently exist. Like you could probably do it with a simple contract on Ethereum today. You could have an arbitrary like two-phase commit.
You don't need any support. I think if you do this on Bitcoin, right? All you need is some agreement that if like the hash of the pre-commit appears in the transaction, that this means a certain thing happened. You need some convention for something committing on Bitcoin triggering an off-chain action or multiple.
And that has to be some protocol, right? Like that has to be a little bit of code somewhere. Yeah.
The only thing you need from the chain is the ability to sign a transaction where the transaction will only be valid until a certain time. So you don't want to pre-commit forever. You need to know that this thing aborted because the expiration time has passed and it never made it into the blockchain.
Yep.
Sorry, and you're using the blocks as your clock in this case?
Well, I was saying, like, most of these blockchains have some kind of time lock feature, right? So you just use whatever is already native to your.
Yeah, I'm pretty sure that the sidechains, that two-way peg, is really just a two-phase commit that just locks money in one side and enables you to unlock money elsewhere.
The problem is like that's a lot more complicated because of the peg, right? You need if you take away the peg, it gets a lot simpler. But the thing is that you actually need to lock up funds on like Bitcoin or whatever, such that those funds are only released when some sidechain. It's like 2-day waiting period.
Right, and what you're describing is you could do this without two-way peg support in either of these by just having that convention that with you and I could do this with two chains that don't do that at all if we use the same convention.
I'm saying like I have like a Postgres database that runs like my rail company. You have a Postgres database that runs your rail company, and we no blockchain at all, but like we want our customers are demanding that we coordinate to do something.
Right.
We said, well, we don't want to coordinate with each other. So instead you say, we'll do this thing where like you can buy from us and for 10 minutes we'll let you lock the thing up and on condition that something happens.
Yeah, that's what I mean in terms of by two chains I meant if I had Bitcoin and you had Stellar, then I could give you Bitcoin for Stellar, and I could send you a transaction from Bitcoin.
Yeah, but for that you could do an atomic cross-chain swap. So I'm thinking like non-blockchain applications. I'm thinking like blockchain can be a two-phase commit driver for non-blockchain transactions. And it suddenly allows this interoperability over systems where you're like, what? How did, you can like, buy a virtual sword in a game and space on a rail car and like, Lufthansa like cargo space, like all in like one transaction, and these things have like nothing to do with one another. And the systems don't know how to interoperate, except that they know how to recognize that they promise something that thing, if on conditions something get committed to blockchain, and they did.
Yep. Cool. Any other questions? Great. Thank you.